Welcome friends to my YouTube channel Soumya Physics. On my previous lecture, I discussed about the efficiency of a Carnot engine, and there we saw that the efficiency solely depends upon source and sink temperature, and it is independent of the nature of the working substance. Okay, so this is the expression of efficiency of a reversible Carnot engine working between the two temperature limits T1 and T2. Okay. Now here few important words that I have to tell. First one is that if we take T1 equal to T2, then this from this expression eta becomes 0. So the engine will not work. Okay, that is engine will not work. So we require two different temperatures so that the engine will work. Okay, so two different temperatures are required. Okay, so first one is that if we take T1 equal to T2, then eta is 0, that is the engine will not work. So for the engine to work, we require two different temperatures. So this is the first thing. And second thing is that if T2 becomes 0, then eta becomes 1, that is efficiency becomes 100%. But this is not possible because practically there is no engine that can have 100% efficiency, so this is not possible. So if eta is 1, that means the entire heat taken from the source is converted to work. Okay, so this is not possible. So this violates second law of thermodynamics. Okay, so these are the important things that I tell here. Now we shall discuss about few limitations of Carnot engine. Okay, so few limitations of Carnot engine that I have to discuss. Okay, that I have to discuss. Okay, so what are the limitations of a Carnot engine? First of all, the concept is purely theoretical. Okay, the concept is purely theoretical. Practically, it is not possible to construct an ideal engine. Okay, so this is the first drawback, that the concept is purely theoretical. And the second is that the output obtained per cycle is very low. Okay, that is we obtain the amount of work expressions, that is in each cycle we obtain the amount of work done or the heat absorbed or heat rejected, so the result is not so good. So the output obtained per cycle is very low. Okay, so these are the two disadvantages of Carnot engine. Okay, you must remember that disadvantages of Carnot engine. Okay, so this is the disadvantage of Carnot engine. Okay, now in our today's lecture I am going to discuss another issue that is called Kelvin scale temperature or absolute scale of temperature. Okay, I am going to discuss the absolute scale of temperature, that is the concept of absolute scale of temperature. Okay, the concept of absolute scale of temperature. Okay, so first of all we have to discuss what is the absolute scale or Kelvin scale temperature. Absolute scale or Kelvin scale temperature, what is it? Now there was a scientist called Lord Kelvin. Okay, Lord Kelvin, by using first and second law of thermodynamics, he invented a new scale of temperature which is independent of the nature of the working substance. That means no matter what we take as working substance, it is totally independent of the nature of the working substance. Okay, so Lord Kelvin, from his study on first and second law, invented this scale of temperature which is independent of the nature of the working substance. Okay, Lord Kelvin invented this new scale of temperature from his study on first and second law of thermodynamics. ঠিক আছে, Lord Kelvin invented this new scale of temperature from his study on first and second law of thermodynamics, which is independent of the nature of the working substance, which is independent of the nature of the working substance. Okay, you must remember it that Lord Kelvin, from his study of first and second law of thermodynamics, invented a new scale of temperature which is independent of nature of the working substance, and this is called absolute scale or Kelvin scale temperature. Now what is the concept behind it? So let's understand the concept behind it. Okay, how this scale was invented theoretically. So let us understand that. Okay, so we know that the efficiency of a reversible engine is a function of source and sink temperature. Okay, that is, we can write this is the efficiency of a reversible Carnot engine where Q1 is the heat absorbed from source, suppose at temperature theta 1, and Q2 is the heat rejected to sink at temperature theta 2. So this is clearly a function of theta 1 and theta 2. Here we introduce the new temperatures theta 1 and theta 2. So at theta 1 temperature the engine absorbs heat from source, and at theta 2 temperature the engine rejects it to sink. So this is, so what will be my Q2 by Q1? 1 minus f of theta 1 theta 2. So what will be my Q1 by Q2? Q1 by Q2 will be 1 by 1 minus f of theta 1 theta 2. So this is a new function that has been generated, so call it, say, capital F theta 1 theta 2. Okay, so this is for a reversible engine that absorbs Q1 heat from source at theta 1 temperature, and rejects Q2 heat to sink at theta 2 temperature. Now if we consider successive reversible engines, then the second engine will absorb that amount of heat which was rejected by the first one. Okay, the second engine will absorb the amount of heat that was rejected by the previous one. So if the second engine absorbs Q2 heat at temperature theta 2 and Q3 heat rejected to sink by second engine at temperature theta 3, so what we can write, f of theta 2 theta 3, this must be what, Q2 upon Q3 for the second engine. So give it a name 2, and the first equation is f theta 1 theta 2, this must be Q1 upon Q2. Okay, so if we multiply these two, then what happened? If we multiply these two, then what happened? If we multiply this, then we get f of theta 1 theta 2 into f of theta 2 theta 3, this must be equal to Q1 upon Q3, and that we can write by using previous, that is this. Okay, so this we can write by using these formulas, we can write Q1 upon Q3, that is f of theta 1 theta 3. Now a close look on this equation, that is equation 3. If we look equation 3, then you will see that in left hand side theta 2 is present in both the terms, where in right hand side theta 2 is absent. Okay, so in left hand side theta 2 is present in two terms, and in right hand side theta 2 is missing. Okay, so when this equality will hold good, this equality will hold good if and only if we write these functions in this way. Okay, that is f theta 1 theta 2, say phi of theta 1 upon phi of theta 2, and f of theta 2 theta 3, this we can write as phi of theta 2 upon phi of theta 3. So if we write these functions in such a manner that phi of theta 2 cancels, then ultimately their multiplication becomes phi of theta 1 by phi of theta 3. So this is theta 1 theta 3. So in this way, if we choose these functions in this way, then this equality will hold good. Okay, so now the equality will hold good. Now the equality holds good. Okay, so now the equality holds good. Okay, so we have to write these functions in such a way that phi of theta 2 and phi of theta 2 cancels, and their multiplication becomes phi of theta 1 upon phi of theta 3, that is f of theta 1 theta 3. Okay, so here we have introduced a new quantity. Okay, so what is it? This is called the Kelvin scale temperature. Okay, here we use a new quantity, and this new quantity is what? Kelvin scale temperature. How? Because we get f of theta 1 theta 2, this we write phi of theta 1 upon phi of theta 2. Now what is my f of theta 1 theta 2? That is q1 upon q2. From previously we get, and we call it tau 1 tau 2. Okay, similarly f of theta 2 theta 3, we can write phi of theta 2 by phi of theta 3. Okay, so that we can write q2 by q3 will be what? q2 upon q3, we can write tau 2 upon tau 3 for the second engine. Okay, here tau is called the thermodynamic absolute scale of temperature, or Kelvin scale temperature. Okay, tau is known as the absolute scale of temperature. Okay, so this is a new concept of temperature. Okay, so in this way the mathematical concept of uh, absolute scale of temperature comes. Okay, so here phi of theta is called absolute scale temperature. Absolute scale of temperature and is denoted by tau. Okay, now we have two scales of temperatures. One is perfect gas scale temperature, one is perfect gas scale, in which we can write for a reversible heat engine Q1 upon Q2, this is equal to T1 by T2, and the second one is Kelvin scale temperature, Kelvin scale, and according to this scale Q1 upon Q2 we can write tau 1 upon tau 2, so from which we can easily conclude T1 upon T2 this is equal to tau 1 upon tau 2. So the ratio of any two temperatures in both the gas scales are equal. So this is one similarity. The ratio of two temperatures on both the gas scales are equal. Ratio of any two temperatures in both scales are equal. Okay, the ratio of any two temperatures in both scales are equal. Okay, so this is one similarity. Okay, this is one similarity. Now let us move to another similarity. So let us try to find out another similarity. So we can clearly find it. Okay, we can clearly find it. The second similarity is that for perfect gas scale we can write Q1 upon Q2 this is equal to T1 upon T2. So if Q2 is 0 then T2 is 0. ঠিক আছে, যে if Q2 is 0 then T2 is 0. So this is one, and in case of a absolute scale we can write Q1 upon Q2 this equals to tau 1 upon tau 2. So here if Q2 equals to 0 that we can write tau 2 equals to 0. So thus again we see that the 0 of two gas scales coincides. Okay, so 0 of two gas scales coincides. What is 0 of Kelvin scale or 0 perfect gas scale? That is the temperature at which the reversible Carnot engine does not reject any heat to sink is called absolute zero temperature. Okay, that it is the temperature of the sink at which the reversible engine does not reject any heat to sink. Okay, this is called zero of two gas scales, that is the temperature at which the reversible Carnot engine does not reject any heat to sink is called zero of absolute scale. Okay, So this is the definition of zero of absolute scale. Okay. Now now in today's video we shall discuss few important discussions on Carnot engine and its limitations, and I always tell about the concept of absolute scale temperature. Okay, and clearly we see that Lord Kelvin, from a study on both the laws of thermodynamics, invented a new scale of temperature which is independent of the nature of the working substance, and we also understand the concept behind it, and we also discuss the similarities between a perfect gas scale and absolute scale. Okay, now I must have to discuss about another issue which is very important. Okay, all of you, that is higher secondary and graduation students, must know this thing. Okay, what is that? We know that the efficiency of a reversible Carnot engine is written in this way. Now there are two ways of increasing the efficiency. Okay, by lowering the sink temperature and by increasing the source temperature. Now which is the best effective way? Okay, which one is more effective, lowering the sink temperature or increasing the source temperature? So let us understand this. So you find out the derivative. At first you do it with respect to T1 by keeping T2 constant. So what we get? So by keeping T2 constant, if we do T1, then the result will be T2 upon T1 square. Okay, now second, you can vary it with respect to T2 by keeping T1 fixed. Okay, so what will be the result? The result will be minus 1 by T1. So if you take the mod d eta dt2 at T1, so what will be the result? 1 upon T1. So this gives a name 1 and this gives a name 2. Now which one is larger? We know that T1 is large. T1 large. Okay. T1 large means T1 square becomes more large and this term becomes small. And here T1 large means T1 square is very large and this term becomes small. And here T1 large, that means this term is less small. Okay, this term is less small because here T1 square, so this term is very small, and here T1, so this term is less small. So we see that this is more effective. So which one? You can vary it with respect to T2 by keeping T1 constant. That means by keeping the source temperature fixed, you must have to vary the sink temperature. That means lowering the sink temperature is the more effective way to increase the efficiency of a Carnot engine. Okay, lowering the sink temperature is the more effective way. You can understand it by simple mathematics. Okay, so lowering the sink temperature is the more effective way to increase the efficiency of a reversible Carnot engine. Okay, so this is what about today. Okay, so in our next class I will discuss about refrigerator. So dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest videos on physics. Thank you.